The Heisenberg uncertainty principle is a fundamental concept in quantum mechanics that has profound implications for our understanding of the subatomic world. The principle, proposed by German physicist Werner Heisenberg in 1927, states that it is impossible to precisely measure both the position and momentum of a particle at the same time. This uncertainty is not a result of limitations in measurement tools, but rather an inherent property of nature itself. At the heart of Heisenberg's uncertainty principle lies the idea that the more accurately we try to measure one property of a particle, the less accurately we can measure another. For example, if we attempt to measure the position of a particle with high precision, we lose precision in measuring its momentum. Conversely, if we focus on determining its momentum, the particle's position becomes less certain. This is not due to any error or imperfection in our instruments, but is a direct consequence of the wave-like nature of particles at the quantum level. The principle was revolutionary because it challenged the classical view of determinism, where it was assumed that all properties of a system could be known precisely given the right tools. In classical mechanics, it was assumed that the position and velocity of an object could be measured simultaneously and precisely. This was true for macroscopic objects, such as cars or planets, where the uncertainty in measurements was negligible. However, when applied to subatomic particles like electrons, this classical notion breaks down. The electron, for example, does not behave as a simple particle with a definite position and momentum. Instead, it behaves as a probability wave, with its position described by a probability distribution. The act of measurement itself affects the system, creating a disturbance that makes precise measurements of both position and momentum impossible. The uncertainty principle has far-reaching consequences for the way we perceive reality. It suggests that the very act of observing the quantum world alters it, making it impossible to achieve a complete, precise understanding of a system. This challenges the classical notion of objective reality, where the properties of an object exist independently of observation. In the quantum realm, particles do not have well-defined properties until they are measured, and even then, those properties are subject to uncertainty. Heisenberg's uncertainty principle introduced a radical departure from classical physics. The principle asserts that uncertainty is not merely a result of experimental limitations, but an intrinsic aspect of the universe itself. The idea that reality is inherently indeterminate at the quantum level has far-reaching philosophical implications. It forces us to reconsider the nature of reality, measurement, and knowledge itself. In addition to its philosophical implications, the uncertainty principle has practical consequences in various fields of physics, including atomic and nuclear physics, chemistry, and even quantum computing. For example, the principle plays a crucial role in understanding the behavior of electrons in atoms. Electrons orbit the nucleus in regions of space called orbitals, which are described by probability distributions. The uncertainty in the position and momentum of electrons helps to explain why electrons do not spiral into the nucleus, as classical physics would predict. The uncertainty principle also underpins the concept of quantum tunneling, where particles can pass through energy barriers that would be insurmountable in classical physics. Furthermore, Heisenberg's principle has led to the development of new technologies, such as the laser and quantum cryptography. These technologies exploit the strange properties of the quantum world, including the uncertainty of particle behavior, to achieve outcomes that were previously thought impossible. The principle also laid the foundation for the field of quantum mechanics, which has become one of the most successful theories in physics, accurately describing the behavior of particles at the smallest scales. One of the key aspects of the uncertainty principle is the mathematical relationship between position and momentum. Heisenberg derived this relationship using the wave-particle duality of matter, which states that particles can exhibit both wave-like and particle-like properties. This duality is encapsulated in the concept of wave functions, which describe the probability distribution of a particle's position and momentum. The uncertainty principle can be expressed mathematically as deltax times deltap is greater than or equal to h, 4 pi, where deltax is the uncertainty in position, deltap is the uncertainty in momentum, and h is Planck's constant. This equation demonstrates that as the uncertainty in one property decreases, the uncertainty in the other must increase. The principle sets a fundamental limit on the precision of measurements, regardless of the technology or methods used. The uncertainty principle has been experimentally verified in many different ways. For example, the diffraction of electrons through a crystal lattice can be used to measure the uncertainty in both position and momentum. Similarly, the principle can be observed in the behavior of particles in particle accelerators, where the position and momentum of particles are difficult to measure simultaneously with high precision. The experimental confirmation of the uncertainty principle has cemented its place as one of the cornerstones of quantum mechanics. Heisenberg's uncertainty principle also plays a significant role in the development of quantum field theory, which is the framework used to describe the interactions of particles and fields in the universe. In quantum field theory, particles are described as excitations of underlying fields, and the uncertainty in their properties reflects the probabilistic nature of these fields. The uncertainty principle has profound implications for our understanding of the universe at its most fundamental level, suggesting that the universe is not a deterministic system, but rather one that operates according to the laws of probability. At the same time, the uncertainty principle also invites a sense of mystery and wonder. It challenges our intuition and forces us to confront the limits of our understanding. The idea that the universe is fundamentally uncertain at its core raises profound questions about the nature of reality, observation, and the relationship between the observer and the observed. It forces us to reconsider the role of measurement in shaping the world around us and highlights the need for a new approach to understanding the universe at its most fundamental level. In the world of quantum mechanics, Heisenberg's uncertainty principle remains one of the most important and influential ideas. It marks a departure from classical physics and opens up new avenues for research and discovery. While the uncertainty principle might seem counterintuitive or even paradoxical, it is an essential concept that has revolutionized our understanding of the quantum world. The principle invites us to embrace the unknown and to recognize that uncertainty is not something to be feared, but something to be understood and explored. It is a reminder that the universe is full of mysteries and that our journey of discovery is only just beginning. The Heisenberg uncertainty principle fundamentally altered our understanding of the quantum world by revealing the inherent limitations of observation and measurement at subatomic scales. It challenges the very foundation of classical mechanics, which held that all properties of a system could be determined precisely if the appropriate tools were available. In the quantum realm, however, Heisenberg's principle shows that these assumptions do not hold. Before Heisenberg's discovery, classical physics assumed that if we knew the position and velocity of an object at one point in time, we could predict its future behavior with absolute certainty. This principle, known as determinism, governed the understanding of macroscopic objects, such as planets and cars, where measurement precision was not an issue. The idea was that the universe operated like a giant clockwork mechanism, where the positions and velocities of all objects could be measured and used to predict their future positions with accuracy. However, quantum mechanics introduced a radically different way of understanding reality. In the quantum world, particles like electrons do not have definite positions or velocities until they are observed. Instead, they exist as probability waves, and only when measured do they collapse into a definite state. Heisenberg's uncertainty principle arose from this fundamental difference, stating that there are limits to how precisely we can know certain properties of particles. The principle does not arise from any flaw in measurement. instruments, or human error, but from the way particles themselves behave at the quantum level. The uncertainty principle can be quantified mathematically, and its implications are significant for many aspects of quantum mechanics. One of the most famous expressions of the principle is the equation deltax times deltap is greater than or equal to h, 4 pi, where deltax represents the uncertainty in position, deltap represents the uncertainty in momentum, and h is Planck's constant. This equation tells us that the product of the uncertainty in position and momentum cannot be smaller than a constant value. In other words, if we decrease the uncertainty in one property, the uncertainty in the other must increase. This relationship highlights the limitations of measurement in the quantum world, where an electron's precise position and momentum cannot be simultaneously known with high accuracy. The discovery of the uncertainty principle radically changed the way physicists understood particles and their behavior. Instead of thinking of particles as tiny, discrete objects with well-defined properties, scientists began to view them as waves of probability. This new understanding helped to explain phenomena that classical physics could not, such as the behavior of electrons in atoms. In particular, the uncertainty principle explained why electrons do not spiral into the nucleus, as classical physics would predict. The uncertainty in the electron's position and momentum keeps it in a stable orbit around the nucleus, instead of allowing it to collapse inward. One of the most profound consequences of the uncertainty principle is its challenge to the concept of determinism. In classical mechanics, if we knew all the initial conditions of a system, we could predict its future behavior with certainty. However, in quantum mechanics, the best we can do is make probabilistic predictions. This shift from a deterministic to a probabilistic view of the universe is one of the defining features of quantum theory. It has led to the development of quantum field theory, which describes the behavior of particles as excitations of underlying fields, and quantum electrodynamics, which explains how light and matter interact at the quantum level. The implications of Heisenberg's uncertainty principle extend beyond theoretical physics. They have practical consequences in various fields, from atomic and nuclear physics to the emerging field of quantum computing. In quantum computing, the uncertainty of quantum states is exploited to perform calculations that would be impossible using classical computers. Quantum bits, or qubits, can exist in multiple states simultaneously, allowing quantum computers to perform parallel computations that would take classical computers an impossibly long time. The ability to harness the principles of quantum mechanics, including the uncertainty principle, could revolutionize fields like cryptography, artificial intelligence, and medicine. Despite its significance, the uncertainty principle also raised philosophical questions about the nature of reality. In classical physics, the world was seen as objective and independent of the observer. A person could observe a system, and the properties of that system would remain unchanged by the act of observation. However, in quantum mechanics, the uncertainty principle suggests that the act of measurement itself affects the system being observed. This has led to debates about the role of the observer in shaping reality, with some interpretations of quantum mechanics suggesting that the observer plays an active role in determining the outcome of measurements. This philosophical issue is still a subject of ongoing discussion among physicists and philosophers. Furthermore, the uncertainty principle has also given rise to a number of thought experiments, such as Schrödinger's cat, which highlight the strange and counterintuitive nature of quantum mechanics. In this thought experiment, a cat is placed in a box with a radioactive atom, and if the atom decays, it triggers the release of poison, killing the cat. According to quantum mechanics, until the box is opened and the system is measured, the cat is in a superposition of both alive and dead states. This paradox highlights the strange implications of the uncertainty principle and the wave-particle duality of matter. The uncertainty principle also has significant consequences for our understanding of time and space. According to general relativity, space and time are interconnected in a four-dimensional fabric known as space-time. The uncertainty principle suggests that at very small scales, the fabric of space-time may become quantized, with discrete units of space and time rather than a continuous, smooth fabric. This concept has led to the development of theories like quantum gravity, which seeks to reconcile quantum mechanics with general relativity and explain the behavior of space-time at the smallest scales. In many ways, Heisenberg's uncertainty principle represents a fundamental shift in our understanding of the universe. It challenges the classical view that the universe is a deterministic system that can be precisely measured and understood. Instead, the uncertainty principle reveals that the universe operates according to probabilistic laws, where uncertainty is not a flaw in measurement, but an intrinsic aspect of nature itself. This insight has not only reshaped the field of physics, but has also led to new technologies and paradigms that continue to shape the modern world. The uncertainty principle is a reminder that, at the deepest levels, the universe is full of mysteries, and our journey of discovery is far from over. The Heisenberg uncertainty principle is one of the cornerstones of quantum mechanics and has had a profound influence on the development of modern physics. Its implications extend far beyond the realm of theoretical physics, shaping everything from atomic theory to emerging technologies like quantum computing. The principle challenges our understanding of the fundamental nature of reality, providing us with a glimpse into the bizarre world of quantum particles, where certainty gives way to probabilities and where observation itself alters the state of the system being observed. One of the most immediate consequences of Heisenberg's uncertainty principle is its challenge to the deterministic view of the universe that had dominated classical physics for centuries. Classical physics, based on the principles of Newtonian mechanics, assumed that if we knew the position and velocity of an object at a given time, we could predict its future motion with complete accuracy. This is known as determinism, and it was an idea that governed not only the behavior of macroscopic objects like planets and cars, but also laid the foundation for the worldview of the 17th and 18th centuries. It was an age of scientific discovery, where the universe was envisioned as a giant clockwork mechanism, operating predictably and precisely. However, the world of the very small, the atomic and subatomic world, does not conform to this deterministic view. In quantum mechanics, particles like electrons do not behave in the same way as larger objects. Instead of having precise positions and velocities that can be measured and predicted, they exist in states of probability. The Heisenberg uncertainty principle revealed that there is an intrinsic limit to how precisely we can measure certain properties of particles. The more precisely we measure the position of a particle, the less precisely we can measure its momentum, and vice versa. This is not due to experimental limitations or flaws in measurement tools, but is a fundamental property of nature. This probabilistic nature of quantum mechanics challenges the deterministic worldview. Rather than thinking of particles as having well-defined positions and velocities, quantum mechanics tells us that particles exist in a cloud of probabilities until measured. The idea that reality is probabilistic rather than deterministic forces us to rethink the very nature of the universe. It means that, at the quantum level, the future is not predetermined and that our understanding of reality is inherently limited by the uncertainty of measurement. One of the key implications of the uncertainty principle is its effect on the concept of causality. In classical mechanics, causality, the idea that every effect has a precise cause, is fundamental. However, in quantum mechanics, the uncertainty principle suggests that causality is not always clear-cut. In the quantum world, events do not necessarily follow a deterministic chain of cause and effect. Instead, events are governed by probabilities, meaning that the outcomes of quantum processes are not fixed but can only be predicted in terms of likelihoods. This does not mean that the laws of physics break down, but rather that the laws of probability govern the behavior of particles at the quantum scale. The uncertainty principle challenges our classical understanding of cause and effect, making it clear that in the quantum world, uncertainty is an inherent aspect of the natural world. The uncertainty principle also has important implications for the concept of measurement in quantum mechanics. In classical physics, measurement is considered an external action that does not affect the system being measured. However, in quantum mechanics, the act of measurement itself alters the system. This is best illustrated by the famous thought experiment known as Schrödinger's cat, where a cat in a sealed box is simultaneously alive and dead until the box is opened and the cat is observed. The uncertainty principle suggests that before the measurement, the state of the system is indeterminate, and only upon observation does it collapse into a specific state. This leads to a phenomenon known as wave function collapse, where the wave function, a mathematical description of the probabilities of a system, collapses into one of its possible outcomes upon measurement. This collapse is not instantaneous, but occurs in a way that cannot be precisely determined. In terms of practical physics, the uncertainty principle plays a crucial role in understanding atomic behavior. For instance, it helps explain why electrons do not spiral into the nucleus of an atom. According to classical physics, an electron should lose energy as it orbits the nucleus and eventually spiral inward. However, quantum mechanics, with the uncertainty principle at its core, explains that the electron's position and momentum cannot both be precisely defined, which prevents it from falling into the nucleus. The electron's behavior is better described by a probability distribution, where it is most likely to be found in specific regions around the nucleus, known as orbitals. This explanation provided by the uncertainty principle helped to reshape atomic theory, providing the foundation for quantum mechanics and modern chemistry. The uncertainty principle also plays a pivotal role in the understanding of quantum tunneling. Quantum tunneling is the phenomenon where particles pass through energy barriers that, according to classical physics, would be insurmountable. In essence, particles in the quantum world can tunnel through barriers, appearing on the other side without having to climb over them. This phenomenon is made possible because of the inherent uncertainty in the particle's position and momentum. Quantum tunneling is essential to many processes in nature, such as nuclear fusion in stars, and is also a key principle behind technologies like tunnel diodes and scanning tunneling microscopes. Another key area where the uncertainty principle plays a role is in the emerging field of quantum computing. Quantum computers, which use qubits, quantum bits, exploit the uncertainty and superposition of quantum states to perform complex calculations far faster than classical computers. In a classical computer, a bit can only be in one of two states, 0 or 1, at any given time. However, in quantum computers, qubits can exist in a superposition of both states simultaneously, thanks to the uncertainty inherent in quantum mechanics. This ability to process multiple possibilities at once allows quantum computers to perform computations that would be practically impossible for classical computers, making them an exciting area of research for fields ranging from cryptography to artificial intelligence. The Heisenberg uncertainty principle is also central to the concept of quantum entanglement, where particles become interconnected in such a way that the state of one particle instantaneously affects the state of another, no matter how far apart they are. This non-local connection between particles challenges our classical understanding of space and time. The uncertainty principle plays a role in understanding how information is transferred between entangled particles and how measurement can influence the outcomes of quantum systems. Quantum entanglement has potential applications in quantum communication and quantum cryptography, where it can be used to ensure secure communication channels. In addition to its role in the development of quantum computing and other quantum technologies, the Heisenberg uncertainty principle also has profound philosophical implications. It challenges the classical notion of objective reality, suggesting that the act of observation shapes the outcome of events. It raises questions about the nature of reality itself, particularly the role of the observer in the physical world. This philosophical shift from a deterministic to a probabilistic universe is one of the defining features of modern physics and has influenced debates in philosophy, particularly in the areas of epistemology and the philosophy of science. In conclusion, the Heisenberg uncertainty principle has had far-reaching implications for both the theoretical and practical aspects of physics. It has reshaped our understanding of the quantum world, challenging the classical, deterministic view and replacing it with a probabilistic framework. From atomic theory to quantum computing, the uncertainty principle has opened up new areas of research and technology, demonstrating the power and complexity of quantum mechanics. Furthermore, it has raised important philosophical questions about the nature of reality and the role of the observer in shaping the world around us. The uncertainty principle is not just a mathematical formula, but a window into the profound mysteries of the universe, reminding us that the world is far more complex and uncertain than we ever imagined. Heisenberg's uncertainty principle is not just a mathematical formulation, it's a profound realization that shapes the very foundation of modern physics. The principle reveals the inherent limitations in measuring the properties of particles at the quantum level, challenging our classical understanding of the universe. It tells us that there are fundamental limits to our knowledge of the microscopic world. These limitations have far-reaching consequences, not only in theoretical physics but also in practical applications across multiple fields, such as quantum computing, chemistry, and even emerging technologies like quantum cryptography. The uncertainty principle challenges the classical worldview, where determinism reigns. In classical mechanics, it was believed that if we knew the position and momentum of an object, we could predict its future state with complete certainty. This deterministic view formed the basis of Newtonian physics, where objects moved in predictable ways under known forces. The idea that the future could be predicted if the present was perfectly known was a powerful and intuitive notion that worked well for macroscopic objects, such as planets and cars. However, the uncertainty principle reveals that, at the quantum scale, this certainty breaks down. In quantum mechanics, particles such as electrons are not considered point-like objects with well-defined positions and momenta. Instead, they are described by wave functions, mathematical functions that give the probability of finding a particle in a particular position or state. This probabilistic nature of particles at the quantum level fundamentally challenges the classical idea of definite properties. The uncertainty principle states that it is impossible to know both the exact position and momentum of a particle at the same time with infinite precision. The more precisely we try to measure one property, the less precise our measurement of the other will be. This limitation arises not because of imperfect measurement tools, but because of the very nature of quantum systems. The implications of Heisenberg's uncertainty principle are profound. The idea that measurement itself influences the system being measured was a groundbreaking revelation. Before the principle, it was assumed that we could observe the world objectively without affecting it. But in the quantum realm, the act of observing a particle disturbs its state, changing the very thing we are trying to measure. This disturbance is not due to technological limitations, but is intrinsic to the nature of quantum systems. The very act of measurement collapses a particle's wave function, reducing the system from a range of probabilities to a single observable outcome. This concept introduces a fundamentally different approach to physics. Instead of determinism, the uncertainty principle introduces a probabilistic interpretation of physical systems. Rather than predicting a precise future trajectory, quantum mechanics allows for the prediction of probabilities and likely outcomes. This probabilistic nature of the quantum world is not something we experience in our everyday lives, where objects follow clear trajectories, but it dominates the behavior of particles at the atomic and subatomic scales. The uncertainty principle also leads to the concept of quantum indeterminacy. While classical physics provides a deterministic view of the universe, quantum mechanics reveals that, at the smallest scales, events unfold in a way that cannot be predicted with absolute certainty. For example, in the double-slit experiment, a particle such as an electron behaves as if it passes through two slits simultaneously, creating an interference pattern typical of waves. However, when the particle is observed, it acts like a particle, passing through one slit only. This duality, wave-like behavior in some circumstances and particle-like behavior in others, demonstrates the indeterminacy at the heart of quantum systems, further reinforcing Heisenberg's uncertainty principle. The relationship between position and momentum in the uncertainty principle also helps explain many phenomena that classical physics could not. One of the most famous applications of the principle is the explanation of why electrons do not collapse into the nucleus of an atom. Classical physics would predict that the electron, moving in an orbit around the nucleus, would lose energy and spiral inward. However, quantum mechanics, guided by the uncertainty principle, shows that the electron's position and momentum cannot be precisely determined at the same time. This uncertainty prevents the electron from collapsing into the nucleus, as its behavior is governed by a probability distribution rather than a definite path. The uncertainty principle is also central to the understanding of quantum tunneling, a phenomenon where particles pass through energy barriers that would be insurmountable in classical physics. For instance, in nuclear fusion, particles inside the Sun overcome the Coulomb barrier, an energy barrier caused by electrostatic repulsion, by tunneling through it. The uncertainty in the particle's position allows it to tunnel through the barrier, leading to fusion reactions. This phenomenon is essential for understanding nuclear reactions in stars and plays a key role in technologies such as tunnel diodes and scanning tunneling microscopes. As the foundation of quantum mechanics, the uncertainty principle has also become integral to the development of quantum field theory, which describes the behavior of particles and fields at the quantum level. Quantum field theory unifies the behavior of particles and the fields they interact with, providing a comprehensive framework for understanding the universe at its most fundamental level. The principle's probabilistic nature allows quantum field theory to describe interactions between particles with a high degree of accuracy, predicting phenomena that have been experimentally verified, such as the interaction of light and matter in quantum electrodynamics. Heisenberg's uncertainty principle is not just a theoretical concept, it has practical implications that have already led to major technological innovations. One of the most exciting areas of development is quantum computing. Quantum computers take advantage of the strange properties of quantum mechanics, such as superposition and entanglement, to perform computations that would be impossible for classical computers. In a quantum computer, qubits, quantum bits, can exist in multiple states at once, thanks to quantum superposition. This ability to explore multiple possibilities simultaneously allows quantum computers to solve complex problems much faster than classical computers. Quantum computing has the potential to revolutionize fields such as cryptography, drug discovery, artificial intelligence, and more. The uncertainty principle also underpins the field of quantum cryptography, where it ensures the security of communications. In quantum cryptography, information is encoded in quantum states, and any attempt to eavesdrop on the communication will disturb the quantum state, revealing the presence of the intruder. This is a direct consequence of the uncertainty principle. The act of measurement changes the state of the system. This ability to detect eavesdropping makes quantum cryptography theoretically secure, even against powerful computational attacks. Furthermore, Heisenberg's uncertainty principle has philosophical implications that challenge our understanding of the nature of reality. The principle suggests that the universe is inherently uncertain at the most fundamental level, and this uncertainty is not just a result of our lack of knowledge, but an intrinsic feature of the world. This view contrasts sharply with the classical idea that the universe operates according to precise, deterministic laws. It raises important questions about the role of the observer in the universe and the nature of objective reality. In the quantum world, the act of observation is integral to the behavior of particles, suggesting that reality itself is not independent of observation. This notion has profound philosophical implications, leading to debates about the nature of consciousness, the role of the observer, and the limits of human knowledge. One of the most remarkable aspects of the uncertainty principle is that it applies universally, not just to microscopic particles but also to larger systems. While the effects of the uncertainty principle are most noticeable at the quantum scale, they also play a role in macroscopic systems. However, at larger scales, the uncertainty becomes negligible because the measurement errors are small compared to the size of the system. For example, the uncertainty in the position and momentum of a baseball is so tiny that it has no practical impact on our ability to measure and predict its motion. This is why classical mechanics still provides accurate predictions for most everyday phenomena. However, the underlying quantum nature of the universe remains a crucial factor in understanding the most fundamental aspects of reality. In conclusion, Heisenberg's uncertainty principle has had far-reaching implications, not only for physics, but also for our understanding of the universe. It has changed the way we think about the nature of reality, observation, and causality. While the principle may seem abstract or counterintuitive, it has provided the foundation for groundbreaking advancements in technology, including quantum computing and quantum cryptography. More than just a scientific concept, the uncertainty principle represents a fundamental shift in our understanding of the world, reminding us that uncertainty and probability are woven into the fabric of the universe at the most fundamental level. The discovery of Heisenberg's uncertainty principle revolutionized the way we view the subatomic world, challenging many classical concepts that had been ingrained in our understanding of physics for centuries. The principle is not just a mathematical equation, but a gateway to a completely different worldview, one that governs the realm of quantum mechanics, where particles behave in ways that defy the logic of our everyday experiences. The uncertainty principle tells us that, at the quantum level, nature is fundamentally indeterminate. The very act of measuring or observing a particle influences its behavior, and this realization opened the door to a new era of scientific thought. To understand the implications of this principle, we must first examine the quantum world and the radical changes in our perceptions it brought about. Before the introduction of the uncertainty principle, classical physics, particularly Newtonian mechanics, assumed a deterministic universe. In this view, if we knew the precise position and momentum of a particle, we could predict its future with absolute certainty. This assumption worked remarkably well for macroscopic objects, like planets and everyday objects, which could be measured with high precision. However, at the subatomic level, this idea began to fall apart. In the quantum realm, particles like electrons are not localized objects with specific positions and momenta. They exist as wave functions, a mathematical representation of a range of possible positions and momenta. These wave functions describe a probability distribution where each possible state of a particle has a certain likelihood, but none of them is absolutely determined until the particle is measured. Heisenberg's uncertainty principle arises directly from this probabilistic nature of quantum mechanics. It states that it is impossible to measure both the position and the momentum of a particle with arbitrary precision simultaneously. The more accurately we measure one of these quantities, the less accurately we can measure the other. This limitation is not due to flaws in our measurement tools or human error, but is an intrinsic feature of the quantum world. For example, if we try to pinpoint the exact position of an electron, the act of measurement introduces an uncertainty in its momentum, and vice versa. The more precisely we try to measure one property, the greater the uncertainty in the other. This radical shift in our understanding of nature upended classical ideas about determinism, whereas classical mechanics treated particles as individual objects with well-defined properties. Quantum mechanics presented a world where uncertainty and probability reigned. Heisenberg's uncertainty principle tells us that at the quantum level, the universe does not behave like a giant clockwork mechanism with predictable outcomes, but instead operates according to the rules of probability. This realization introduced a fundamental shift in our scientific worldview, as it suggested that the universe at its core is governed by indeterminacy, not certainty. The implications of this shift were not just theoretical, but had practical consequences across various branches of physics and technology. For instance, the uncertainty principle explained why electrons in atoms do not collapse into the nucleus, a problem that had puzzled scientists for years. According to classical physics, the electron should continuously lose energy and spiral inward, eventually crashing into the nucleus. However, the uncertainty principle tells us that the electron's position and momentum cannot both be precisely determined, which prevents the electron from falling into the nucleus. Instead, the electron occupies a cloud of probabilities, with its position described by a probability distribution known as an orbital. This understanding of atomic structure laid the foundation for the development of quantum mechanics and revolutionized our approach to chemistry and atomic physics. Similarly, the uncertainty principle played a key role in explaining phenomena such as quantum tunneling, where particles pass through energy barriers that would be insurmountable in classical mechanics. In nuclear fusion, for example, the uncertainty principle allows particles to tunnel through the Coulomb barrier, which is the repulsive force between positively charged nuclei. This is the mechanism behind the energy produced by stars, including our Sun. Without the uncertainty principle, the process of fusion would not be possible, as particles would not be able to overcome the electrostatic barrier. One of the most fascinating aspects of quantum mechanics, and one that directly stems from the uncertainty principle, is the phenomenon of quantum entanglement. When two particles become entangled, their properties become linked in such a way that measuring one particle instantly affects the state of the other, no matter how far apart they are. This spooky action at a distance, as Einstein famously called it, challenges our classical understanding of space and time. In entangled systems, the act of measurement on one particle appears to communicate information to the other particle, instantly changing its state. The uncertainty principle underpins this behavior, as it highlights the fundamental non-locality of quantum systems. When particles are entangled, their measurements are not independent, but are deeply connected, regardless of the distance between them. In the realm of quantum computing, the uncertainty principle is a critical concept that allows quantum computers to process information in ways that classical computers cannot. Quantum computers utilize quantum bits, or qubits, which, due to the principles of superposition and entanglement, can exist in multiple states simultaneously. This ability to handle multiple possibilities at once allows quantum computers to solve complex problems exponentially faster than classical computers. While the uncertainty principle limits the precision of measurements in quantum systems, it also enables the power of quantum computation, as quantum systems exploit the uncertainty in ways that classical systems cannot. Moreover, the uncertainty principle has philosophical implications that challenge our traditional understanding of reality. In classical physics, objects are considered to have definite properties independent of observation. A particle has a position, momentum, and energy, and these properties exist whether or not we measure them. However, in the quantum world, the uncertainty principle tells us that these properties are not well defined until we measure them. The act of measurement itself alters the system, which leads to questions about the nature of reality and the role of the observer. Some interpretations of quantum mechanics, such as the Copenhagen interpretation, suggest that the observer plays an active role in determining the state of the system. This has led to philosophical debates about the nature of existence, perception, and the limits of human knowledge. The uncertainty principle also influenced the development of quantum field theory, which describes the fundamental forces and particles of nature as excitations of underlying fields. In this framework, particles are not seen as independent objects, but as manifestations of fields that exist throughout space. The uncertainty principle plays a crucial role in quantum field theory, as it governs the interactions between particles and fields. It also helps explain phenomena, such as vacuum fluctuations, where particles spontaneously appear and disappear in empty space due to the uncertainty in energy. Quantum field theory has become the dominant framework for understanding particle physics and has led to the development of the Standard Model, which describes the electromagnetic, weak, and strong nuclear forces. Finally, Heisenberg's uncertainty principle has far-reaching implications in our understanding of the fundamental nature of the universe. It suggests that the universe is inherently probabilistic, not deterministic. While classical mechanics relied on the idea that the future of a system could be predicted precisely if its initial conditions were known, quantum mechanics shows us that this is not possible. At the quantum level, the future is uncertain, and the best we can do is predict probabilities rather than certainties. This realization has profound implications for our understanding of the cosmos, suggesting that uncertainty and indeterminacy are not just features of quantum systems but are woven into the fabric of reality itself. In conclusion, Heisenberg's uncertainty principle is one of the most important and influential concepts in modern physics. It has reshaped our understanding of the quantum world, revealing a universe governed by probability and uncertainty rather than determinism. The principle has provided explanations for phenomena that classical physics could not, from atomic structure to quantum tunneling. It has also opened up new fields of study, such as quantum computing and quantum cryptography, and raised important philosophical questions about the nature of reality and the role of the observer. The uncertainty principle is not just a theoretical concept, but a key to unlocking the mysteries of the universe at its most fundamental level. Heisenberg's uncertainty principle is more than just a principle in quantum mechanics, it is a radical shift in our understanding of reality itself. The principle states that there is an inherent limitation in the precision with which certain pairs of physical properties of a particle, such as its position and momentum, can be simultaneously known. This restriction is not due to the imperfection of our measurement tools or observational methods, but rather is a fundamental feature of the quantum world. In this sense, the uncertainty principle highlights the very limits of human knowledge when it comes to the behavior of subatomic particles, challenging centuries of classical physics. The introduction of the uncertainty principle in 1927 by Werner Heisenberg marked a significant departure from classical physics, which was based on deterministic laws. Classical mechanics, which had been established by Newton and further developed by physicists like Maxwell and Faraday, was grounded in the belief that the universe followed precise and predictable laws. If we could measure the position and velocity of a particle, we could predict its future trajectory with absolute certainty. This determinism worked perfectly well for macroscopic objects, planets, cars, and even baseballs, where the uncertainty in measurements was negligible. However, this classical view began to falter when applied to atomic and subatomic particles, where the scale of uncertainty was no longer negligible. At the heart of quantum mechanics is the understanding that particles, such as electrons, are not like tiny billiard balls that travel along well-defined paths. Instead, they exhibit both particle-like and wave-like behaviors. This duality means that particles are described by probability waves that tell us the likelihood of finding a particle at a particular position, rather than a definite location. The uncertainty principle arises from this wave-particle duality, stating that the more precisely we know the position of a particle, the less precisely we can know its momentum, and vice versa. This is not due to any technical limitations in measurement devices, but is a fundamental feature of quantum systems. One of the most profound implications of the uncertainty principle is its challenge to the classical idea of causality. Classical physics relied heavily on the concept that every effect had a specific cause, and that if we knew the initial conditions of a system, we could predict its future evolution with certainty. This deterministic worldview was deeply ingrained in the scientific thought of the 19th century. However, in quantum mechanics, the uncertainty principle introduces a probabilistic framework where we can no longer predict specific outcomes with certainty, only the likelihood of different outcomes occurring. This is not to say that quantum mechanics is random, but rather that the universe at the quantum level operates according to probability, not determinism. The future of a quantum system is not determined in a precise way, but rather described by a range of possible outcomes, each with a certain probability. This shift to probabilistic thinking was a difficult pill to swallow for many physicists of the time, including Albert Einstein. Einstein, who had been one of the pioneers of quantum theory, famously said, "God does not play dice with the universe," expressing his discomfort with the idea that nature itself was governed by chance. Despite Einstein's reservations, experiments and observations have consistently confirmed the validity of the uncertainty principle and the probabilistic nature of quantum systems. This is particularly evident in the famous double-slit experiment, where particles like electrons exhibit interference patterns typically associated with waves, even when fired one at a time. When observed, the particles behave like particles, but without observation, they behave like waves, existing in multiple states simultaneously. The uncertainty principle helps explain this behavior, as the act of measurement forces the particle to choose a definite state. The uncertainty principle also profoundly affects our understanding of atomic and molecular structure. In classical mechanics, an electron orbiting an atomic nucleus was thought to behave like a planet orbiting the Sun, with a clearly defined position and momentum. However, quantum mechanics, with its probabilistic approach, explains that the electron's position and momentum cannot be simultaneously known with absolute precision. Instead, the electron exists in a cloud of probability, with its position described by a probability distribution known as an orbital. The uncertainty in the electron's position prevents it from collapsing into the nucleus, as classical physics would predict. The uncertainty principle provides a natural explanation for the stability of atoms and the existence of chemical bonding, leading to the development of quantum chemistry, which is central to modern chemistry and material science. Beyond the realm of atomic physics, the uncertainty principle has far-reaching implications for our understanding of space and time. One of the most exciting areas of research in theoretical physics today is the attempt to reconcile quantum mechanics with Einstein's theory of general relativity, which describes the force of gravity and the fabric of space-time. Heisenberg's uncertainty principle suggests that space and time may not be continuous at the smallest scales, but instead may be quantized, with discrete units of space and time that cannot be divided further. This idea forms the basis of quantum gravity, a field that seeks to understand the behavior of spacetime at the Planck scale, where the effects of both quantum mechanics and gravity are significant. This quest for a unified theory of quantum gravity remains one of the biggest challenges in modern physics. The uncertainty principle is also foundational to the development of quantum technologies that are revolutionizing the modern world. One of the most promising areas of research is quantum computing, where the principles of superposition and entanglement allow quantum computers to solve problems that would be infeasible for classical computers. In a classical computer, a bit can represent only one of two states, 0 or 1, at a given time. In contrast, a qubit in a quantum computer can represent both 0 and 1 simultaneously, thanks to the principle of superposition. This ability to perform multiple calculations at once exponentially increases the computational power of quantum computers. The uncertainty principle underpins this ability, as quantum computers rely on the probabilistic nature of quantum states to perform calculations in parallel. Similarly, quantum cryptography, which uses the principles of quantum mechanics to secure communications, exploits the uncertainty principle. In quantum key distribution, information is encoded in quantum states, and any attempt to eavesdrop on the communication will disturb the quantum state, revealing the presence of the intruder. This principle ensures the security of quantum communications, as it is impossible to measure quantum information without disturbing it, making it ideal for secure communication networks. In addition to its practical applications, the uncertainty principle also has profound philosophical implications. It forces us to reconsider our understanding of reality, measurement, and knowledge. Classical physics assumed that the world existed independently of our observation and that we could uncover its secrets by measuring its properties. In contrast, quantum mechanics suggests that reality is not objective in the classical sense, but is instead influenced by observation. The uncertainty principle implies that there is no objective reality in the quantum world, only probabilities that become fixed when measured. This realization raises fundamental questions about the nature of the universe and our role as observers within it. If the act of measurement shapes the reality we experience, what does this say about the nature of existence itself? The uncertainty principle also challenges the classical idea of causality. In classical mechanics, events unfold in a chain of cause and effect, and the past determines the future. However, in quantum mechanics, causality is not so straightforward. Quantum events are governed by probabilities, and while we can predict the likelihood of different outcomes, we cannot predict specific events with absolute certainty. This probabilistic view of causality challenges our intuition and leads to new ways of thinking about time and the nature of the universe. In conclusion, Heisenberg's uncertainty principle has had far-reaching consequences for our understanding of the universe. It has transformed quantum mechanics from a theoretical abstraction into a powerful framework for describing the behavior of particles at the smallest scales. The principle has reshaped our view of space, time, and causality, leading to new technologies such as quantum computing and quantum cryptography. It has also opened up philosophical debates about the nature of reality and the role of the observer in shaping the world around us. The uncertainty principle is not just a cornerstone of modern physics, but a profound insight into the nature of the universe, reminding us that uncertainty, not certainty, is at the heart of the quantum world. The uncertainty principle, a foundational concept in quantum mechanics, asserts that there are inherent limits to how precisely we can know certain pairs of physical properties of a particle, such as position and momentum. This principle is not a result of measurement imperfections or technological limitations, but a fundamental feature of the quantum world. When we attempt to measure one property with higher precision, the other property becomes more uncertain. The principle challenges the deterministic worldview of classical mechanics, where it was assumed that precise measurements of an object's position and momentum could allow for exact predictions of its future behavior. In contrast, quantum mechanics embraces probabilistic behavior, emphasizing the intrinsic uncertainty present in nature. The implications of the uncertainty principle are vast, extending beyond theoretical physics to influence fields such as quantum computing, cryptography, and even our philosophical understanding of reality. One of the most profound implications of the uncertainty principle is its challenge to the classical notion of determinism. Classical mechanics, founded by Newton, operated under the assumption that if all the forces acting on a system were known, one could predict the system's future behavior with precision. This deterministic view worked well for macroscopic objects like planets, cars, and projectiles. However, At the subatomic level, particles like electrons do not follow fixed trajectories, but instead exist as probability distributions. The uncertainty principle reinforces this by revealing that we can never know both the exact position and momentum of a particle simultaneously with infinite precision. This probabilistic nature of quantum systems upends the classical idea that the future is a predictable, deterministic sequence of events. Instead, quantum mechanics suggests that the universe operates under the laws of probability, not certainty. The uncertainty principle also has significant consequences for our understanding of atomic structure. In classical physics, it was assumed that an electron orbiting an atomic nucleus would behave like a planet orbiting the Sun. If the electron were to lose energy, it would spiral inward toward the nucleus. However, quantum mechanics, guided by the uncertainty principle, explains that the electron does not have a well-defined position or momentum. Instead, it exists in a cloud of probability, with its exact position described by an orbital, a region where it is most likely to be found. This understanding prevents the electron from collapsing into the nucleus. The probabilistic nature of the electron's location is a direct consequence of the uncertainty principle, and it helps explain the stability of atoms and the structure of the periodic table. Without the uncertainty principle, the very existence of matter as we know it would not be possible. In addition to its impact on atomic theory, the uncertainty principle has profound implications for the understanding of quantum phenomena like tunneling. Quantum tunneling is the phenomenon where particles pass through energy barriers that, according to classical physics, should be insurmountable. The principle explains that due to the uncertainty in the particle's position and momentum, particles can tunnel through barriers, appearing on the other side without having to overcome them in the traditional sense. This behavior is essential to understanding nuclear fusion in stars, where hydrogen nuclei fuse to form helium, releasing energy. In fact, the process that powers the Sun and other stars relies on quantum tunneling, made possible by the uncertainty principle. Tunneling also plays a role in technologies such as scanning tunneling microscopes, which allow scientists to observe individual atoms by exploiting the principles of quantum mechanics. Another important consequence of the uncertainty principle is its role in the development of quantum technologies, particularly quantum computing and quantum cryptography. Quantum computing utilizes the principles of superposition and entanglement, both of which are linked to the uncertainty in quantum states. In classical computing, a bit can be in one of two states, either 0 or 1, but quantum bits, or qubits, can exist in multiple states simultaneously. This ability to perform calculations in parallel, thanks to quantum superposition, allows quantum computers to solve certain problems exponentially faster than classical computers. The uncertainty principle underpins this by ensuring that quantum systems can exist in multiple possibilities at once, enabling the computation of solutions to problems that would be intractable for classical systems. Additionally, quantum cryptography exploits the uncertainty principle to create secure communication channels. In quantum key distribution, the transmission of information is protected by the principle that any attempt to eavesdrop on the quantum states being transmitted will disturb those states, revealing the presence of the intruder. This ensures that quantum cryptography provides a level of security that classical encryption methods cannot achieve. The uncertainty principle thus not only shapes our theoretical understanding of the quantum world, but also drives advancements in emerging technologies that are poised to revolutionize fields such as computing, communication, and security. The Heisenberg uncertainty principle is one of the cornerstones of quantum mechanics, introducing a fundamental limit to how precisely certain properties of a particle, such as position and momentum, can be known. The principle was introduced by Werner Heisenberg in 1927 challenging the deterministic worldview that prevailed in classical mechanics. In classical physics, it was believed that with precise measurements of an object's position and velocity, one could predict its future behavior with certainty. However, Heisenberg's discovery showed that, at the quantum level, the more accurately we measure one property of a particle, the less accurately we can measure the other. This relationship is a direct result of the wave-like nature of particles at the microscopic level. The uncertainty principle thus forces a departure from classical ideas and opens the door to a probabilistic understanding of the quantum world. One of the most significant implications of the uncertainty principle is its challenge to the concept of determinism. In classical mechanics, the behavior of an object was thought to be predictable if all the forces acting on it were known. This assumption worked for macroscopic objects, such as planets or everyday items, where the uncertainty in measurements was so small that it had no practical impact. However, at the quantum level, particles do not follow fixed deterministic paths. Instead, they exist as probability waves, with only a likelihood of being found in a particular position or momentum. The uncertainty principle reflects this uncertainty, indicating that the precise position and momentum of a particle cannot be known simultaneously with infinite accuracy. The shift from determinism to probabilistic behavior marks a fundamental change in how we understand the universe, particularly at the subatomic level. The uncertainty principle also plays a crucial role in explaining atomic structure. In classical physics, it was assumed that an electron orbiting the nucleus of an atom would behave like a planet orbiting the sun. If the electron were to lose energy, it should spiral inward and eventually collide with the nucleus. However, quantum mechanics, guided by the uncertainty principle, provides a different explanation. Electrons are not in fixed orbits, but instead exist in regions of probability known as orbitals. These orbitals describe the likelihood of finding an electron in a particular region around the nucleus. The uncertainty principle explains why electrons do not collapse into the nucleus, because the electron's position and momentum cannot both be precisely determined. It remains in a stable orbit, with its position governed by a probability distribution rather than a definite path. This understanding helps explain the structure of atoms and the stability of matter itself. Another major impact of the uncertainty principle is its role in quantum tunneling. Quantum tunneling is the phenomenon where particles can pass through barriers that, according to classical physics, would be insurmountable. This behavior is made possible because of the uncertainty in a particle's position and momentum. Quantum mechanics allows particles to tunnel through energy barriers by virtue of their wave-like properties. The uncertainty principle helps explain why particles can seemingly defy classical physics by moving through these barriers. Tunneling is responsible for several key physical phenomena, including nuclear fusion in stars, where particles overcome the Coulomb barrier, electrostatic repulsion between positive charges, to fuse together, releasing enormous amounts of energy. Without the uncertainty principle, the process of fusion would not be possible, as classical physics would not allow particles to pass through such barriers. The uncertainty principle is also central to the development of quantum technologies. One of the most exciting applications of quantum mechanics is in the field of quantum computing. Unlike classical computers, which use bits that can represent either a 0 or 1, quantum computers use quantum bits, or qubits. Due to the uncertainty principle, qubits can exist in a superposition of both 0 and 1 at the same time. This ability to handle multiple possibilities simultaneously allows quantum computers to process information much faster than classical computers. This is especially useful in solving complex problems, such as simulating molecular interactions or factoring large numbers, tasks that would take classical computers an impractical amount of time to complete. The uncertainty principle is essential for quantum computing because it underpins the idea that quantum systems can exist in multiple states at once, leading to a dramatic increase in computational power. Furthermore, the uncertainty principle has important implications for quantum cryptography, which leverages quantum mechanics to create secure communication systems. In quantum key distribution, the uncertainty principle ensures the security of information by making it impossible to measure quantum information without disturbing the system. If someone attempts to intercept a quantum communication, the act of measurement will alter the quantum states, alerting the sender and receiver to the presence of the intruder. This makes quantum cryptography fundamentally more secure than classical encryption methods, as it guarantees that the information cannot be intercepted without detection. The uncertainty principle thus plays a key role in the development of secure communication channels, which could revolutionize industries such as banking, national security, and private communications. In conclusion, Heisenberg's uncertainty principle has had far-reaching implications for both theoretical and practical aspects of physics. It has reshaped our understanding of the subatomic world, challenging classical determinism and introducing a probabilistic view of reality. The principle helps explain the structure of atoms, the behavior of particles in quantum mechanics, and the phenomenon of quantum tunneling. It has also spurred the development of groundbreaking technologies such as quantum computing and quantum cryptography. More than just a mathematical expression, the uncertainty principle represents a profound shift in our understanding of the universe, reminding us that uncertainty is not just a feature of quantum systems, but an intrinsic aspect of the natural world. The Heisenberg uncertainty principle, introduced by Werner Heisenberg in 1927, fundamentally altered our understanding of the quantum world, presenting a stark contrast to the deterministic laws of classical mechanics. Classical physics, particularly the mechanics developed by Newton, relied on the idea that if we knew the exact position and velocity of an object at any given time, we could predict its future trajectory with certainty. This deterministic worldview worked well for large objects, such as planets or cars, where measurement precision was not an issue. However, the behavior of particles at the quantum level does not adhere to this predictable pattern. Instead, quantum mechanics revealed a universe governed by uncertainty and probability, where the future behavior of particles cannot be determined precisely. At the heart of the uncertainty principle is the concept that certain pairs of properties, such as position and momentum, cannot both be precisely measured at the same time. The more accurately we measure one property, the less precisely we can know the other. This inherent uncertainty is not due to flaws in measurement techniques, but is a direct result of the wave-particle duality that governs quantum systems. According to this duality, particles, such as electrons, exhibit both particle-like and wave-like characteristics. When we try to measure a particle's position, we force it into a localized state, making its momentum uncertain, and vice versa. This is a fundamental characteristic of quantum systems, suggesting that nature itself is probabilistic rather than deterministic at the smallest scales. The uncertainty principle has far-reaching implications for our understanding of atomic structure. In classical mechanics, it was assumed that electrons orbit the nucleus of an atom in well-defined paths, similar to how planets orbit the sun. If an electron lost energy, it was expected to spiral inward toward the nucleus. However, quantum mechanics, guided by the uncertainty principle, explains that electrons do not travel in fixed orbits. Instead, they exist in regions around the nucleus where they are most likely to be found. These regions are known as orbitals. The electron's position is described by a probability distribution, meaning it can be anywhere within that orbital at any given moment. The uncertainty principle helps to explain why electrons do not collapse into the nucleus, as the uncertainty in their position and momentum prevents them from following classical trajectories. In addition to its role in explaining atomic structure, the uncertainty principle plays a critical role in the phenomenon of quantum tunneling. Quantum tunneling occurs when particles pass through potential barriers that they would not be able to cross according to classical physics. This phenomenon is essential in processes such as nuclear fusion, where atomic nuclei combine to form heavier elements, releasing vast amounts of energy. In stars, including our Sun, quantum tunneling allows hydrogen nuclei to overcome the Coulomb barrier, the repulsive electrostatic force between positively charged particles, and fuse together. The uncertainty principle allows particles to exist in a superposition of states, giving them the ability to tunnel through energy barriers. Without the uncertainty principle, the process of fusion and the energy production in stars would not be possible. The uncertainty principle is also central to the development of quantum technologies, particularly quantum computing. Quantum computers operate on quantum bits, or qubits, which are fundamentally different from classical bits. While a classical bit can be either 0 or 1, a qubit can exist in a superposition of both states simultaneously, thanks to the uncertainty inherent in quantum systems. This superposition allows quantum computers to perform calculations in parallel, dramatically increasing computational power. The uncertainty principle is integral to quantum computing because it enables qubits to exist in multiple states at once, rather than being limited to a single state like classical bits. This ability to handle multiple possibilities simultaneously allows quantum computers to solve problems much faster than traditional computers, particularly in fields like cryptography, optimization, and artificial intelligence. Another crucial application of the uncertainty principle is in quantum cryptography, which leverages the strange properties of quantum mechanics to create secure communication systems. In quantum key distribution, information is encoded in quantum states, and the uncertainty principle ensures that any attempt to intercept or measure the information will disturb the quantum states being transmitted. This disturbance reveals the presence of the eavesdropper, making it impossible to steal information without detection. The uncertainty principle guarantees the security of quantum cryptography by ensuring that the very act of measurement changes the system, providing an inherent level of protection against unauthorized access. The philosophical implications of the uncertainty principle are profound. In classical physics, it was assumed that the universe operated according to precise, deterministic laws. The uncertainty principle, however, suggests that the universe at its most fundamental level is indeterminate, governed by probabilities rather than certainties. This realization has led to a major shift in our understanding of reality, challenging the idea of an objective world independent of observation. In quantum mechanics, the act of observation itself influences the outcome, a concept that has sparked debates about the nature of consciousness and the role of the observer in shaping reality. Some interpretations of quantum mechanics, such as the Copenhagen interpretation, suggest that particles do not have well-defined properties until they are measured. This has led to philosophical questions about the relationship between the observer and the observed, as well as the limits of human knowledge. In summary, Heisenberg's uncertainty principle has revolutionized our understanding of the quantum world, challenging classical ideas about determinism, observation, and causality. It provides a new framework for understanding the behavior of particles at the smallest scales, leading to groundbreaking discoveries in atomic structure, quantum tunneling, and the development of quantum technologies like computing and cryptography. The principle not only reshapes our scientific worldview, but also invites deep philosophical reflection about the nature of reality and the limits of human knowledge. It reminds us that, at the most fundamental level, the universe is governed by uncertainty, and the more we seek to understand it, the more we are confronted with the profound mysteries of the quantum world. The Heisenberg uncertainty principle, a cornerstone of quantum mechanics, reshapes our understanding of the physical world. Introduced by Werner Heisenberg in 1927, the principle challenges classical ideas of determinism, revealing that at the quantum level, certain pairs of properties, like position and momentum, cannot be known simultaneously with perfect precision. This intrinsic uncertainty is not a result of measurement errors or technological limitations, but is a fundamental characteristic of the quantum realm. The more precisely we measure one property of a particle, the less precisely we can measure the other, a relationship that lies at the heart of quantum mechanics and distinguishes it from classical physics. Before the uncertainty principle, classical mechanics operated under a deterministic framework. It was assumed that if we knew the position and velocity of an object at any given time, we could predict its future trajectory with absolute certainty. This concept worked well for macroscopic objects like cars or planets, where the precision of measurements did not introduce any significant uncertainties. However, at the subatomic level, this worldview breaks down. In the quantum world, particles such as electrons do not follow precise paths. Instead, they exist as probability waves, with a range of potential positions and momenta. The uncertainty principle captures this probabilistic nature, showing that the universe behaves differently at the smallest scales, where particles are not governed by deterministic laws but by probabilities. One of the key consequences of the uncertainty principle is its impact on our understanding of atomic structure. Classical physics could not explain why electrons in an atom do not spiral into the nucleus, as classical electromagnetic theory predicted. According to classical physics, an electron should lose energy as it orbits the nucleus, eventually collapsing into the nucleus itself. However, the uncertainty principle provides an answer. It tells us that we cannot precisely know both the position and momentum of an electron at the same time. This uncertainty prevents the electron from collapsing into the nucleus. Instead, electrons exist in orbitals, probability clouds that describe the likelihood of finding an electron in a given region of space. This understanding is essential for the development of quantum mechanics and atomic theory, explaining why atoms are stable and how chemical bonds form. The uncertainty principle also plays a pivotal role in the phenomenon of quantum tunneling, which occurs when particles pass through energy barriers that classical physics would deem insurmountable. For example, in nuclear fusion, the uncertainty principle allows particles like protons to tunnel through the Coulomb barrier, the repulsive electrostatic force between positively charged particles. Quantum tunneling is the key to understanding the energy produced by stars, including our Sun. Without the uncertainty principle, this process would not be possible, as classical physics could not explain how particles could overcome such energy barriers. Tunneling also has practical applications in technologies such as tunnel diodes and scanning tunneling microscopes, where it allows for the precise measurement of atomic structures. In addition to its theoretical importance, the uncertainty principle has practical consequences in modern technology, particularly in the realm of quantum computing. Quantum computers leverage the properties of quantum mechanics, such as superposition and entanglement, to process information in fundamentally new ways. Unlike classical computers, which use bits that can be either 0 or 1, quantum computers use qubits, which can exist in both states simultaneously due to superposition. This allows quantum computers to perform calculations on a massive scale, solving problems that would be intractable for classical computers. The uncertainty principle underpins this ability, as it allows qubits to exist in multiple states at once, greatly enhancing computational power. Another key application of the uncertainty principle is in the field of quantum cryptography, which uses quantum mechanics to ensure secure communication. Quantum key distribution, a technique used in quantum cryptography, exploits the uncertainty principle to create unbreakable encryption. When information is transmitted using quantum states, Any attempt to measure or intercept the information disturbs the quantum state, alerting the sender and receiver to the presence of the eavesdropper. This ability to detect eavesdropping makes quantum cryptography theoretically secure, as it guarantees that the information cannot be stolen without detection. This has profound implications for fields such as secure communications and data protection, offering a new level of security that classical encryption methods cannot match. Beyond its implications in technology and atomic theory, the uncertainty principle also challenges our philosophical understanding of reality. Classical physics treated the universe as objective and independent of the observer. The properties of objects were thought to exist whether or not we observed them. However, quantum mechanics, through the uncertainty principle, suggests that the very act of observation affects the system being observed. In quantum mechanics, particles do not have definite properties until they are measured. This idea raises profound questions about the nature of reality and the role of the observer. It suggests that reality at the quantum level is not fixed or objective, but is shaped by observation, leading to debates about the role of consciousness in determining the state of the universe. The uncertainty principle also has implications for our understanding of causality. Classical physics was built on the idea that events are causally linked, that every effect has a specific cause, and the future is determined by the present. However, in quantum mechanics, the uncertainty principle reveals that causality is not so straightforward. Quantum events are governed by probabilities, and while we can predict the likelihood of different outcomes, we cannot predict specific events with certainty. This challenges the classical view of a deterministic universe and suggests that at the quantum level, causality operates differently, governed by the laws of probability rather than certainty. This probabilistic nature of quantum mechanics has led to the development of new interpretations of quantum theory, such as the Copenhagen interpretation, which suggests that the act of measurement causes the collapse of a quantum state into a definite outcome. In summary, Heisenberg's uncertainty principle has transformed our understanding of the universe. It has revealed that at the quantum level, uncertainty is an intrinsic feature of nature, and that the universe operates according to probabilistic laws rather than deterministic ones. The principle has provided crucial insights into atomic structure, quantum tunneling, and the behavior of particles, while also spurring the development of groundbreaking technologies like quantum computing and quantum cryptography. Beyond its practical applications, the uncertainty principle has deep philosophical implications, challenging our ideas about observation, reality, and causality. In a world that is increasingly governed by quantum mechanics, the uncertainty principle serves as a reminder that uncertainty, rather than certainty, is the fundamental characteristic of the quantum realm.